in the last, basically so far we have made the formalism, how to write down the Navier-Stokes equation, compute energy transfers, compute the flux, right, the formalism of flux. So, we can also compute the flux given the Navier-Stokes equation. I can compute energy transfers, but you need a profile, right. Given velocity field, we can compute flux, right. I mean SKPQ and sum it up. But now we are going to do some theory. So, given a profile, of course I can compute flux, but I like to know what happens in nature. Like for example, in the atmosphere, there is a flow. Is there some property of the flux? Okay, and turns out it is not very complicated. We can understand what should be the nature of flux, or what should be the nature of spectrum or energy of the Fourier modes. We can compute them, or we can give a theory of it. Okay. So, that first theory was by Kolmogorov, which I will discuss right now. First theory for flux in spectrum. Okay. Of course, there were many fluid dynamics is very old subject. So, there were a lot of work in other directions, but turbulence flux was by Kolmogorov, which I am going to discuss in today's lecture. So, energy spectrum and flux for 3D hydrodynamics. We will find that 2D hydrodynamics or MHD, magnetohydrodynamics or convection, they have different behavior, but all of them you start from Kolmogorov theory or the formalism of Kolmogorov theory and see how they are different. Okay. So, it becomes a cornerstone, like the starting point for other fields as well, including plasma turbulence and so on. Wave turbulence, like water waves, ocean, there is a turbulence in that. So, a lot of it starts from here, then you make modifications or you, but idea of flux is very important. I mean, I will show you how it is. So, the outline for this set of lectures will be, I will derive the Kolmogorov theory, I will just explain what it is. In fact, I will derive it, okay, but in our own way. It is slightly different than, well, it is a bit different than what Kolmogorov did, but it is a different, but the result is the same. Okay. So, insights from Kolmogorov theory, what can you say about fluid? So, we can say more things, then numerical verification. So, I will not get into experiments, but in computer simulations we can find the flux and the spectrum, and we find that it is very similar to what Kolmogorov predicts, and then limitation of Kolmogorov theory, and we can also generalize it to dissipation range and to also laminar theory. Okay. So, this is the outline. So, we will do it probably in 2 lectures. So, let us start with Kolmogorov theories for 3D hydrodynamic turbulence. Okay. So, this equation everybody has seen, no, I mean we derived it, but this is my, for me this is very important equation. Okay. So, this k, by the way, is a radius of the sphere, wave number sphere, right. So, for a shell, so this is shell spectrum, not a mode spectrum. How do I convert mode to shell spectrum to from the mode spectrum? I just sum over all the modes within the shell, right. There are many modes in the shell. It has radius k, and for in computer simulation we make the radius as 1, but in real life radius, well, I mean computer simulation, because I said in last class, you remember my dk is 1, but in general there is a wave numbers will have distance. You can choose dk as a variable, dk, difference between the radius of the 2 circles. So, here ek is basically is defined in the following way, because we need it for Kolmogorov theory. Integral ek dk is a total energy if I sum over 0 to infinity. Okay. What is this guy? It is basically how to compute it. I take a shell of radius dk, it has energy, divide that by dk. So, ek is energy in the shell of radius dk of width dk divide by dk, and make dk go into 0 limit. Okay, so, that will be a shell spectrum, and that is what Kolmogorov's 5-third theory is. So, we should know exactly what is dEk. So, what is the dimension of Ek by the way? In Kolmogorov theory or in physics language, since I divide by dk, so it is going to be energy dimension. So, this is the dimension, right, energy dimension divide by dimension of k. So, that will be k is dimension of 1 by length. So, this is dimension of energy times length, or energy is what is velocity squared. So, I am not keeping mass in it, okay. Mass is 1. So, it is L squared by T squared. So, this is dimension of L cube by T squared, okay. So, that is what is meant by energy shell spectrum. You must understand this. This is not energy within energy of the shell, but energy of the shell divided by its thickness. For computer simulation, like in our code, we make dk as 1 more quite often. If it is not, then you divide by the width, okay. Now, so this is energy of a shell. Well, it is not really a shell, but I mean I have divided by dk throughout, okay. So, this is like in calculus, no, you divide by delta x. So, this is a density. So, energy in the shell is, as I told in the earlier classes, it can change by the flux. If flux goes out, then energy decreases in the shell. So, this is, by the way, so we also, now this we need to remember. So, let me just make this figure a bit bigger. I have in the next slide, but I just want you to keep this in mind. This is shell energy changing. So, the two fluxes, flux coming from the inner shell, inner sphere, and flux going from the outer sphere. It should be the difference of the flux. Flux is always for a sphere, and I did tell you in the past that this flux is not like a flux energy going out per unit time per unit area. It is a scalar quantity, it is not a vector quantity. It is total energy coming out of the sphere per unit time, okay. So, it is a difference in the flux for the radius dk divided by dk. This we derived in the earlier classes, okay. So, this is a, that is why this is a partial derivative. Now, this function of both k and t, things can change in time. So, that is why we have this partial t partial k for time being, okay. Now, what is this? So, energy can also change in a shell by some external force. External force could be buoyancy or some magnetic force, you know, there could be lots of forces that can change the energy of a shell, or it could change by dissipation. So, dissipation always will decrease the energy. So, this duk is negative, minus duk will decrease. So, duk is positive, but minus duk is negative. So, we derived these formulas in the past. So, Fk is, I am summing over all the modes in the shell. So, force multiplied by velocity, right, that is energy, power basically, this power input in the shell. And it is, Kolmogorov assumes that we force the large scale, okay. This is an assumption which is made in Kolmogorov theory. So, what does it mean? I take a bucket of water and stir using a big stick like this at large scale. You do not force at small scale. Okay. It is possible that I can force at small scale. I mean, I have charged particles, I shine electromagnetic field, that will force at small scales, but that is not what Kolmogorov theory is. Kolmogorov theory says I force the large scale, and large scale means size of the box, of the order of size of the box. It could be 1/5, half, like that, but it is box size. So, it is important to keep in mind large scale, and we divide, we make a notation is Kf is the forcing scale with order of 1 by length of, and L is the box size, capital L is box size. Now, what about dissipation? So, dissipation is defined like this, 2 nu k squared Ek, right, we did in the past. Now, you see this, now EUK, I do not know the function, but EUK normally we know in fluids that it will be some kind of energy is large at large scale, but it keeps decreasing. This will decrease with k. So, k squared is a positive, k squared is increasing function. It turns out all of this one, this quantity is k to the power alpha, alpha is positive for intermediate and large case. So, that means this function is increasing with k, du k increases with k. Okay. So, dissipation is more and more if you go to higher and higher k, and that basically comes from the gradient, you know, omega squared. This is coming from the grad square is giving you k square. Okay. So, at small scale the gradients become stronger and stronger. Okay. So, dissipation is active, more and more active at large scales, is not active at small scale in hydrodynamic turbulence. Okay. Situation may be different in other physical systems, but in hydro 3D, if I take a bucket of water, stir it very fast, then you find that it is only that this is situation. So, this is active more at small scales, and so I am going to make a picture. So, I am going to show you what this means. Okay. Just wait for the next set of slides. Okay. Now, in this equation I am going to take some limits. So, we have forcing as well as dissipation. So, let us assume that I wait for some time, so that the force the system becomes quasi equilibrium. That means, this energy of the shell fluctuates, but fluctuates around a mean. If you wait for some time, you keep stirring it, then bucket water will keep, average energy will be constant. It will fluctuate in time, but it is average energy. This is called steady state. Okay. But it is not steady state in the sense it is constant, but it is steady state in the sense its average is constant. Okay. So, make this assumption steady state where I can drop the d by dt term. Okay. This is fluctuating, this one, but is changing very slowly. So, I drop it. So, what do I get? Now, my t dependence is gone. Okay. So, I make a, now instead of partial derivative, I make a ordinary derivative or total derivative like this. So, this term is gone. So, I get d pi by dk is this. So, under steady state energy flux. So, you know, so this one. So, this is a flux. So, the incident flux and the outgoing flux. So, they need not be equal. So, if outgoing flux is more than ingoing flux under steady state, how is this possible? I mean, my energy, this energy does not change here. No? So, if somebody is like giving more money to people, you know, donation or whatever, so it is guaranteed that that person has more income and less spending, otherwise they can't sustain it, right. So, what does it mean? If this is positive, then my Fu must be bigger than du from this equation is straightforward, right. So, Fu is earning and du is dissipation, spending. Okay. So, and pi u is like giving to others or taking from others. Okay. So, this is like taking in the left arrow, and this is giving to others, you know. So, this is what is. So, if you give more, then that means you must have more income under steady state. Okay. So, this equation for flux. So, in fact, I call this variable energy flux. It is a very nice idea. It is a very simple idea, but it is a very useful idea. You can really say a lot with this. Now, I make an assumption of the inertial range. What is the inertial range? So, I define two ranges. One is forcing scale, where forcing function will be determining the fluid behavior. Like in bucket, I just stir this. So, at large scale there is a forcing. So, that is how I stir it, that will determine the energy at that scale. The small scale where dissipation is more active. Dissipation is everywhere, but dissipation is strong at small scales, but there is a range of scales in between. Okay. That is called inertial range, and is under an assumption that inertial range does not know much about forcing, neither about dissipation. So, inertial range is a universal function. The spectrum in the inertial range is a universal function, that is independent of forcing as well as independent of dissipation. Okay. So, well, I mean, you can see it kind of intuitively in what I am going to say. So, there is a scale in between. So, we have forcing, this is a wave number. Okay. So, a small scale will be forcing, a small k, sorry, small k, large scale, and this is a dissipation, this is f and this is a dissipation. So, in between range what happens? In between forcing is off, here there is no forcing, right, in this band, no forcing, and also dissipation is weak. So, in the inertial range I can say that both are negligible. So, my d pi by dk is 0. So, my flux will be constant, and this is assumption of Kolmogorov theory, well, it is a derivation of a Kolmogorov theory in fact. So, if from energetics I can say the flux will be constant. Of course, flux is fluctuating, but on the average it will be constant. So, this d pi by, so as a function of k, flux cannot change. So, d pi, this is my conclusion in the inertial range, and I am not really making any assumption really. I start from energetics and it derive flux must be constant. But as I said, this flux will be fluctuating in time. So, if I just take this flux, it will fluctuate time, but if I just ignore the fluctuation, then my mean value average to a slightly longer time is constant. So, this is what is drawn here. So, this flux in the sphere, a flux into the shell, sorry, not sphere, this flux out going out of the shell, and shell has radius dk, this is dk. This is a shell, is my pink region in the shell, it is a 3D, it is a cut. Okay. So, its radius is dk. Now, I make this in this, if it is k is in the inertial range, then my injection by external force is 0. This is assumption now by Kolmogorov theory that I force only the large scale, not the intermediate scale. So, this is what I force only the large scale. So, you see this is k is a 1 by length. So, I force to the left this region, some region, well, not be all region, but it is in the left. This is where dissipation is strong, dissipation. So, this KDI is where dissipation starts to become very dominant, and K eta I am going to define where basically kinetic energy is very small after K equal to K eta. So, this region has hardly any kinetic energy. So, I was telling the last class, no, the energy spectrum if I draw, then energy is almost 0 for K greater than K eta. So, this region has negligible energy. Now, negligible in computer simulation will be 10 power minus 8 in non-dimensional units. Okay. So, this is the region where flux is constant, and this is called inertial range. So, this inertial range is here, dissipation range, this is called dissipation range or dissipative range, and this is the forcing range. Okay. So, we know that flux must be constant. So, it is true in a bucket of water I supply energy at large scale, then it is cascading. Cascade means is going down in scale, okay, and it is not going down in real life, I mean in real space. If you look at this, there is no energy going, it is going from one scale to other scale. In some sense it is very similar to money flowing from large scale to rich people to small middle class, then to small. So, it is going down like that. So, very similar analogy, and at very small scale there is a transfer to heat, and after that scale there is no kinetic energy. So, if you look at a zoomed view of the velocity field, you see this big vortex, then smaller vortex, but after some time it just becomes a fuzzy blob. There is no definition of velocity field at that scale. Okay, it just a diffused structure at very tiny scale, and you can't define velocity if there is no motion, large scale motion. Well, I will not say large, there is no motion at, there is no visible motion. Now, visible need not be my eye, but visible is like if I make a coarse grained picture in continuum picture, I take many 50 particles and see whether there is a mean flow. If there is no mean flow at that scale, then you say 0 velocity. Okay. So, this is the k eta. Now, I will not discuss this, but this is interesting physics. This is not my mean free path length of the particles. Please do not mistake this one. This is not kinetic mean free path length. It is where my velocity field loses meaning. That is what is k eta. Okay. So, we will define k eta. I mean, I am going to come to it a bit later. So, it is just that my velocity field u of k eta is tending to 0. That is my definition of k eta. It is very tiny. Now, given flux, can I get a formula for the spectrum? Okay. Now, what do I do? One idea is to use dimensional analysis. Okay. So, let us do dimensional analysis. So, it is just very straightforward from here. So, what is the dimension of EU of k? So, dimension is this, no? I derived this, I told you in the last slide, L cube by T squared. Now, what could EU depend on? So, let us see EU. Now, we make an assumption that in this intermediate range flux is constant. I say I believe that it will not depend on how I force the system. Okay, it is irrespective of forcing. And also it does not depend on how it is dissipated, how energy is dissipated. So, it is independent of viscosity or how kinetic energy is being dissipated. So, it does not depend on viscosity as well. So, it can depend on this flux which is cascading down. So, it has the information of how much energy is being fed at large scale, which is cascading down, because locally I know this is coming down and where it goes through me. So, any scale shell knows that how much it is cascading down. Okay. So, it has information about how much flux is going through. So, k to the power, well, k to the power beta, and local wave number is local scale, no. So, it depends on k. So, k to the power alpha. So, these two quantities I assume is an assumption that depends on flux and local wave number. It does not depend on viscosity, it does not depend on forcing. This is why it is called universal. Now, if I can find it. Now, what is dimension of? So, I will do dimensional analysis. Okay. What is dimension of k? Is 1 by length. And what is dimension of pi? Pi u. It is energy by time, is energy supply rate, no. So, energy is L squared by T squared and divide by time. So, T cube. So, it is L squared by T cube. Okay. So, let us just do the matching now. So, left hand side is L cube by T squared, right side is k to the alpha will be 1 by L to the alpha, and pi is L square to beta T 3 beta. So, what does it tell you about beta right away? So, T squared must match with T 3 beta. So, that means beta is 2 by 3, and beta is 2 by 3, that means I should get alpha right away. So, 3 equal to minus alpha plus 2 beta. So, alpha equal to 2 beta minus 3 is 4 by 3 minus 3 is minus 5 by 3. So, alpha is minus 5 by 3, beta is 2 by 3. So, I can write down the formula for energy spectrum. EU of k is phi 2/3 k minus phi 3rd, and there is a constant. Is a dimensional analysis does not tell you about constant, but there is a non-dimensional constant, and it is called Kolmogorov constant. Ko means Kolmogorov. Okay. So, this is my formula for the energy. This is a prediction for the energy spectrum formula from this energetics argument, derived from dimensional analysis, but it is great. I mean, so it turns out this formula works for all flows as long as it is hydrodynamic. If I put magnetic field, there is some indication that it, so that is different part, okay, MHD or convection. So, somewhere also it works, but in hydrodynamics in 3D it works. People have done experiments on ocean, atmosphere, in labs, in various wind tunnel stuff. So, this is seen everywhere, and that is why it is called, it is independent of your forcing mechanism, how viscous. So whether I turn like this, turn like that, or two left, two right, it does not matter how you do it, this will always be there. Or whether it is water or air or liquid helium or whatever fluid, viscosity is not in this. So, it is independent of which fluid you apply. So, it is like Newton's law. Okay. So, Newton's law does not care whether you are applying Newton's law to stone or to star, or so Newton's law works at classical scale. So, this is a universal theory, that means it works for all fluids. All fluids means hydrodynamic, okay, with water, mercury, and it works for all sorts of forcing in the intermediate range, not in the forcing range. So, when in the picture which I had shown before, so there is a forcing band, there is a dissipation band in K. So, in this band there will be minus 5/3 in the intermediate, okay, and this region could be depend on forcing, this region could also depend on dissipation. So, but intermediate will be minus 5/3. This Kolmogorov constant has also been calculated by experiment, simulation, and also by theory. There is a theory, field theory, it is around 1.6 to 1.7. Okay. So, these are not like fine structure constant, or in turbulence we can't get a number with some 3 decimal places, it does not work. Okay. There are fluctuations, there are effects of the forcing. So, this is not very precise. Okay. So, any questions on this?
Constant is also not sensitive to the system.
No. Okay, I must say that in real life, of course, there is a dependence on. So, I am going to show you this theory has its own limitations. It is not exact theory. Okay, there are some. So, if I make experiment on a grid and simulation, then this Kolmogorov depends on what grid resolution I am using, but that is experimental limitation. What Kolmogorov says that nu going to 0 limit, that means Reynolds number going to infinity limit, this is true, but no experiment can claim that I am infinite Reynolds number, right. Asymptotically you have to wait for steady state. So, this is a mathematics theory really. So, in experiment there always will be some difference, but in any experiment, even though they claim great accuracy, every experiment has experimental error bars and so on. Okay. So, this is a theory of Kolmogorov, which is this is called 5/3 theory. The spectrum is minus 5/3. Now, so let us do some more analysis. So, about the flux. Now, under steady state, so this is the under steady state. This is formula I just showed you in the last slide. If I do the integral over full space, full wave number space, so what happens to this? 0 to infinity. So, there will be flux at infinity minus flux at 0. So, what is flux at infinity? 0, because there is no mode outside to give energy to, right. I mean, there is basically nobody, no taker of your modes. So, flux at infinity is 0, flux at 0 is also 0, there is no mode to give. At infinity there is no mode to take, and at 0 there is no mode to give. So, left hand side will be 0. So, this integral, FU integral must match with du integral. So, this integral is the energy supply rate. So, my energy is supplied at by external forcing. Okay. So, that is energy supply rate, and what is this integral? 0 to infinity is a dissipation. So, under steady state is obvious that whatever I supply energy must be balanced by total dissipation, but this must be 0 to infinity. Okay. So, this is exact result. And now we call epsilon u the dissipation rate, this total dissipation rate. Now, I can do some more. So, the region where there is no force. So, I start from the region where, so this was forcing here. So, I start from K naught where force is not there anymore. Okay. So, this is I turn off the forcing. No, force is, well, no, I do not turn it off. I go to the wave number region where forcing is 0 for K greater than K naught. Kf is a forcing wave number which is to the left of K naught. So, Kf is here. So, you can see that Kf is less than K naught. Okay. So, let us go now. I will integrate this, but I integrate from K naught to infinity. So, this is integrated from K naught to infinity. So, that will give you pi infinity minus pi K naught. So, that will give pi K naught, pi infinity is 0, and pi K naught is the constant. Well, I assume that the flux has already become constant. Okay. So, flux, this is where flux is constant. So, I want to relate the flux with the dissipation rate. This is relating input energy with output energy, this one, but I want to relate it to flux. So, so this constant flux, this is equal to pi u K naught where forcing is basically not affecting anymore. So, this must be this integral. Now, this integral is K naught to infinity, this one is not 0 to infinity. That means pi u is, so there is a condition which we get, epsilon u is bigger than pi u, right, because epsilon u is a 0 to infinity integral and du is always positive. So, I can say that epsilon u must be bigger than pi u, because pi u is K naught to infinity integral and epsilon u is 0 to infinity integral. So, in simulations we should test whether, you must keep in mind that epsilon u must be bigger, your flux will be always smaller than epsilon u. Okay. Flux will fluctuate a bit, but flux does not really fluctuate a lot in simulations, because averaged over many modes. Okay. So, this is one condition which I encourage students to test when you do the code. Okay. So, I think this is about the first set of slides. Okay. Thank you.